In Memoriam, Alexander Grothendieck, 1928 to 2014, as raved by the last sober lunatic, in a world of cowards and calculators. When the going gets weird, the weird turn pro. Hunter S. Thompson, Jesus Christ on a cracked-out blackboard. What was that thing that just tore through the 20th century like a flaming Mobius strip made of logic, vodka, and pure abstraction? A man? A mystic? A mushroom hallucination in the head of God? No, it was Grothendieck. Alexander fucking Grothendieck. The last real thing to crawl out of the rotted anus of post-war Europe and scream truth into the shriveled eardrums of a cowardly, weaponized academia. They say he was a mathematician, but that's like saying Nietzsche was a life coach. No, he was more than that. A conceptual terrorist. A metaphysical vandal. A man so far off the intellectual map, he had to build his own coordinate system to come home, and then burn the map. He tore holes in mathematical space and crawled through them barefoot, chewing on set theory and spitting out galaxies. The early madness. Born in 1928 in Berlin, baptized in blood, baptized in chaos, the spawn of anarchists and poets, his father a Russian Jew with a taste for prison and revolution, his mother a walking Molotov cocktail of intellect and ideology. They named him Alexander, as if preordaining his fate to conquer something. But what he conquered was reality itself, flayed and redrawn from the empty set upward. He bounced through Europe like a photon in a madhouse, Montpellier, Paris, anywhere the bastards would let him learn. But he didn't learn. He devoured. They gave him integral calculus. He turned it into a Lovecraftian beast and fed it to a new geometry. He wasn't learning math. He was unmaking it and stitching it back together with cleaner stitches. And soon he found them. The Bourbakistas, cloaked in abstraction and pure logic, hiding behind a pseudonym like a French mathematical Illuminati. He joined them, or infected them, or maybe he consumed them from the inside out. Because what he did with the Bourbaki vision made their collective work look like kindergarten glue and poster board projects. The high empire of abstraction. By the time the rest of us were learning how to spell cohomology, Grothendieck had detonated algebraic geometry and reconstructed it from his own psychic excrement. He didn't solve problems. He made new worlds where problems didn't exist. Only structures, floating in an infinite platonic vacuum, stitched together by sheaves and topoi and fucking motives. Schemes, my friend. Schemes. Not plans. Not plots. Schemes like post-spacetime lenses, mathematical LSD tabs that let you see how a curve in 3-space might just be a ghost of something 12-dimensional, purring quietly behind the veil of perception. By 1966, the establishment gave him the Fields Medal, the Nobel Prize of Mathematics. But the son of a bitch refused to go get it. Why? Because it was being handed out in Soviet Moscow, and he had no time for totalitarianism. Not red, not blue, not even chartreuse. He would not have his hands shaken by goons who jailed poets. Instead, he went to Vietnam. Yes, Nam, the jungle, the bombs, the screams, and in the middle of it, this bearded prophet, barefoot in the mud, giving math lectures to Vietnamese students under the sound of napalm whistling overhead. You think your life has purpose? Try explaining e-tail cohomology while the jungle is on fire and your chalk melts in the heat of God's wrath. The great refusal. Eventually, he returned to France and took the throne at the IHS. the closest thing the West had to an Olympian mathematical temple. He ruled like a deranged high priest of abstraction. The seminars were legendary. New gods were born there, Grothendieck's ideas, his descends d'enfants, his categories and universal properties. Mathematics had become ritual magic, and he was the magus. And then he quit. Why? Because IHS took money from the French military. That's it. That's all. Some backroom handshake between suits and generals, and Grothendieck threw his kingdom into the sea. He was done. Not with math. With the world. CERN and the last revolt. He sniffed around CERN for a while, like a coyote in a particle zoo, not to bless the Higgs boson or jerk off over quarks, but to spy. He wanted to understand what had become of the scientific enterprise. His verdict? It was dead. Science had been sold, packaged, militarized, fed into the great black hole of bureaucratic nihilism. The ideal of knowledge, of pure truth, had been compromised beyond salvation. He saw the beast and refused to ride it. He wrote screeds, thousands of pages, not dry theorems, but metaphysical manifestos, recoltes et semails, la clef de songes, part poetry, part prophecy, part ravings from a man who had stared into the structure of the universe and saw only shadows of shadows. The vanishing. Then he disappeared. Gone. Like Rimbaud, like Lao Tzu, like fucking Obi-Wan into the desert. He wandered into the Pyrenees, took a cabin, and wrapped himself in vegetable tinctures and divine silence. No more visitors. No mail. No interviews. They say his house filled with jars of roots, plants, alchemical slop brewed from forest mushrooms and gut wounds of the earth. Manuscripts written in microscopic script. He stopped publishing. He started talking to angels, or maybe category theorists from the 11th dimension. One day, he asked a friend for a gun, to kill himself. Not because he was depressed, but because he saw no exit from the lie of consensus reality. Because the soul of mathematics had been sold to the war machine. Because no one was listening. Or maybe because he saw the structure collapsing and wanted out before it imploded. We'll never know. Because he didn't die then. He died in silence many years later, in 2014, in an anonymous bed, far from any blackboard, far from any institution, just a man and his ghosts and the flowers that outlived him. The man and the myth. Alexander Grothendieck is not a man anymore. He is a vector field of pure defiance, a topology of exile, a goddamn singularity in the history of thought. He proved nothing that could be printed in the Times. No sexy prime number records. No smooth four-dimensional spheres. No cute TED Talk summaries. But he broke reality and gave us the pieces. He wanted to find the roots of mathematics, but what he found were the roots of being, and they terrified him. And us. He walked away because we weren't ready. So here's to Grothendieck. May your soul, if you have one, be busy redefining the ontology of heaven. May your spirit roam in the upper reaches of an infinite-dimensional topos, laughing at our petty axioms. May the category of your ghost remain non-trivial and eternally a joint to truth. You weren't crazy, Alex. You were just ahead of the goddamn curve. Rest in paradox, you magnificent bastard. Eulogy written by Hunter S. Thompson, under the influence of coffee, morphine, and the collected letters of Abel. Dedicated to all who still dream in the language of mathematics.
Postscriptum. Grothendieck and string theory, or how a reclusive mathematician reshaped the conceptual foundations of modern physics without ever entering a lab. Introduction: The Alchemist of Abstraction. Alexander Grothendieck was perhaps the most enigmatic and transformative figure in 20th century mathematics. Born in 1928 to anarchist parents, his father a Russian Jewish revolutionary, his mother a German writer, Grothendieck's early life was marked by dislocation, political upheaval, and war. He spent part of his childhood interned in a Nazi camp in France, and his father perished in Auschwitz. From this journey of suffering emerged a mind of unparalleled originality and radical independence. By the 1950s and 60s, Grothendieck had completely transformed the field of algebraic geometry, a cornerstone of pure mathematics concerned with the solutions of polynomial equations. But Grothendieck didn't merely solve problems. He reinvented the very language in which mathematics could be conducted. He introduced entire galaxies of new concepts: schemes, functors, sheaves, categories, topoi, and motives. These were not technical tricks but conceptual revolutions, radically expanding the terrain of the mathematical imagination. He worked obsessively, almost mystically, often in marathon bursts of thought, redefining the structures of mathematics from the ground up. At the height of his career, he was more than a mathematician. He was a visionary, reshaping mathematics as if he were building a new metaphysical cosmos. Yet in the 1970s, Grothendieck suddenly withdrew from professional mathematics. He refused awards, including the Fields Medal. He abandoned his prestigious position at the Institut de Hautes Études Scientifiques, IHS, citing its military funding. Over time, he retreated from public life altogether, spending his final decades in spiritual isolation in the French Pyrenees, pursuing metaphysical writings and correspondence with few. Despite his absence from the mainstream of theoretical physics, Grothendieck's work came to underlie some of the most sophisticated ideas in modern string theory. The irony is profound. A man who rejected physics as intellectually shallow and ethically compromised ended up providing the mathematical framework within which the most advanced physical theories are now articulated. This article explores how Grothendieck's abstract constructions, originally motivated by deep problems in number theory and geometry, turned out to be foundational for the development, formalization, and philosophical depth of string theory. In doing so, it reveals how the language of pure mathematics, when pushed to its highest levels of abstraction, can ultimately become the scaffolding for our deepest theories of space, time, and matter. Introduction: Bridging Worlds. The story of string theory is often told through the lens of physics. It begins with the dream of unifying the fundamental forces of nature and culminates in an esoteric framework in which particles are replaced by vibrating strings, existing in 10 or 11 dimensions. What is less commonly appreciated is that the maturation of string theory was not only a triumph of physical intuition but also of abstract mathematics. And among the mathematical giants who, without directly working in physics, laid the groundwork for its theoretical architecture, none is more enigmatic, transformative, or foundational than Alexander Grothendieck. Grothendieck did not contribute a single equation to string theory. He did not write papers on supersymmetry, compactification, or dualities. In fact, he harbored an aversion to the physics of his time, finding it philosophically shallow and mathematically crude. Yet his pioneering work in algebraic geometry, category theory, and topos theory redefined the conceptual landscape in which modern theoretical physics operates. Grothendieck's influence is that of a secret architect, designing structures so general and profound that others, decades later, could build in them the palaces of high-energy physics. This article aims to chart the influence of Grothendieck's ideas on string theory research. It will do so in plain language, avoiding technical formulations, and focusing instead on the philosophical and conceptual revolutions he introduced. It is a story not just about mathematics or physics, but about the power of abstraction to shape our understanding of reality itself. Part 1. Grothendieck's Revolution, a New Way of Seeing Mathematics. To understand Grothendieck's influence, we must begin with his central mission, to reimagine the very language of mathematics. In the mid-20th century, mathematics was compartmentalized. Algebra, geometry, topology, and number theory were largely separate domains, connected in spirit but not in form. Grothendieck shattered those walls by developing unifying concepts that could describe all these domains simultaneously. The cornerstone of his vision was the idea of categories, mathematical universes where objects, like sets, spaces, or groups, are defined not by their internal structure but by the relationships, morphisms, between them. From this idea emerged the powerful tools of functors, natural transformations, and eventually topoi, plural of topos, which generalize the notion of space itself. His reformulation of algebraic geometry, a field that studies the solutions to polynomial equations, was so revolutionary that it essentially created a new field. Grothendieck replaced the older idea of solving equations with the concept of schemes, which allowed for far more general and abstract spaces, including those where classical intuition fails. This abstraction allowed mathematics to deal with spaces that are not made of points in the usual sense, yet retain enough structure to be studied rigorously. Grothendieck's approach was metamathematical. He was more concerned with the underlying languages and frameworks of mathematics than with solving particular problems. In doing so, he created a formal universe flexible enough to absorb future theories that had not yet been imagined, including string theory. Part 2. The Geometrization of Physics. For much of the 20th century, physics and geometry were intimately linked. Einstein's general theory of relativity had taught physicists to think of gravity as the curvature of spacetime. But in quantum physics, geometry seemed to take a back seat. The tools of quantum field theory were largely analytic and computational, relying on perturbation expansions and path integrals, often with little regard for rigorous mathematical foundations. String theory changed that. From its inception, string theory demanded a radically geometrical approach. Instead of particles, one studies one-dimensional strings that trace out two-dimensional surfaces, worldsheets, in higher dimensional space. These surfaces behave like Riemann surfaces, objects studied extensively in complex geometry. As the theory developed, it incorporated higher dimensional analogues called branes, Calabi-Yau manifolds, and moduli spaces, concepts drawn directly from sophisticated branches of modern geometry and topology. This is where Grothendieck's legacy begins to assert itself. The machinery developed in his reformulation of algebraic geometry turned out to be essential for formalizing the mathematical structures of string theory. Part 3. Moduli spaces, stacks, and the language of dualities. One of Grothendieck's key contributions was the concept of moduli spaces, mathematical spaces that parameterize families of other objects. For example, instead of studying a single geometric shape, one studies the space of all such shapes, with parameters that describe their deformations. This idea is indispensable in string theory, where different shapes of compactified extra dimensions correspond to different possible vacua of the universe. But Grothendieck went further. He realized that moduli spaces in general are too naive to capture all the subtleties. Sometimes, one must account not just for the shapes themselves but for how they are related, even in the presence of symmetries and degeneracies. To deal with this, he introduced the notion of stacks, which generalize moduli spaces and allow a more refined treatment of geometric objects that have automorphisms. In string theory, stacks are used in the formulation of orbifolds, string backgrounds with singularities, and in the stringy geometry of mirror symmetry, a central duality that relates seemingly different Calabi-Yau spaces. The mathematical formulation of mirror symmetry, particularly through the homological mirror symmetry conjecture proposed by Maxim Kontsevich, relies heavily on derived categories and functorial methods directly inspired by Grothendieck's approach. In this sense, Grothendieck's ideas provide the mathematical language of string dualities. These dualities, between large and small compact dimensions, T-duality, between strong and weak couplings, S-duality, or between different geometric spaces, mirror symmetry, are not just physical curiosities. They are structural symmetries of the theory that suggest a deep, underlying unity. Grothendieck's categorical thinking, which emphasizes relationships over components, is uniquely suited to capturing these symmetries. Part 4. Topos theory and quantum geometry. One of Grothendieck's most philosophically profound ideas was topos theory. A topos is a generalized space that can support logical reasoning and geometric structure. It is a kind of mathematical universe in which one can do geometry with new, often non-classical, notions of point and space. Although topos theory has not yet been fully integrated into mainstream string theory, it represents one of the most promising frontiers for the future of quantum geometry. In attempts to reconcile quantum mechanics and general relativity, researchers increasingly suspect that spacetime itself may be emergent, that is, it arises from deeper, pre-geometric structures. Topos theory provides a framework for spaces without points, which can model such emergent behaviors. Some speculative proposals have suggested that quantum spacetime might best be described by a kind of non-commutative or topos-theoretic geometry. In such a picture, classical spacetime is merely an approximation, much like a fluid is an approximation of molecules in motion. Grothendieck's vision of spaces as sheaf-theoretic constructions, rather than point sets, gives the mathematical foundation for such pre-spacetime regimes. Moreover, recent work on categorical quantum mechanics and higher topos theory, fields with growing relevance to quantum gravity and topological string theories, draw directly on Grothendieck's structuralist approach. Part 5. Philosophical resonance. Grothendieck's vision of reality. Beyond technical contributions, Grothendieck's philosophy resonates deeply with the spirit of string theory. He believed that the deepest truths were hidden in the patterns of relationships, not in isolated entities. He often spoke of the rising sea method. Rather than attacking problems head-on, one should slowly raise the level of abstraction until the problem dissolves in a new perspective. This is precisely what string theory does. By reimagining particles as vibrations of higher dimensional objects, it dissolves the sharp distinctions between forces, between geometry and matter, even between space and time. The theory is not a final answer, but a vast web of interconnected dualities, consistent only when seen as a whole. This holistic view mirrors Grothendieck's own understanding of mathematics, not as a collection of truths, but as a living ecosystem of relations. Grothendieck saw mathematics as a spiritual journey, one of inner transformation and metaphysical clarity. He abandoned the mathematical world in his later life to live in isolation, searching for deeper truths. While string theorists remain embedded in empirical science, many have noted the quasi-mystical aura of the theory, a framework so rich, so symmetric, so eerily unified, that it seems less like a human invention and more like a pre-existing Platonic form. Conclusion: the hidden architect. In the history of science, there are visible builders and invisible architects. Alexander Grothendieck was the latter. His work does not appear in the standard textbooks of physics, but the very possibility of a mathematically rigorous string theory depends on the language he created. Without his reimagination of geometry, moduli spaces and stacks would not exist in their current form. Without his emphasis on categories and relationships, mirror symmetry and dualities would lack their formal expression. And without his vision of abstraction as revelation, the metaphysical aspirations of string theory, its attempt to glimpse the code of the cosmos, would be intellectually impoverished. Grothendieck remains an anomaly, a man who transformed the architecture of mathematics while barely acknowledging physics. Yet, in a poetic twist, his mathematical cathedral became the temple in which physicists now seek the theory of everything. As string theory continues to evolve, Grothendieck's influence will only deepen. His legacy reminds us that the most profound discoveries often emerge not from solving old problems, but from redefining the very space in which those problems exist.